trend through what letters you're hearing. And I'm like, I'm not sure if that's the voice or just the letters.
How often do you have to do that? I think it's like
Yeah, you like watch it.
Yeah, you have to watch it. You have to pay attention to it.
And then you have to wait for them to reset it. Yeah.
All right, so any questions from last time? All right, well, let's talk about other ways to tackle syntax. So this is something called BNF, Bacchus-Naur form. It's a standard way to describe the syntax of a language. And you can find BNF for, the C language or Java or Python or other languages like that. And if you know the BNF for a language, it's pretty easy to get a start on writing something like a compiler for that language, at least as far as checking the syntax. Because this basically tells you exactly what is or is not a part of the language. And you can use this to do analysis to tell if something is syntactically valid, and you could use it to do synthesis, to create words or sentences that are valid in a language. And the general form of a BNF is a series of expressions. So they generally have the form of the name of some type of expression inside angle brackets. And then there's usually 2 colons and an equal sign, but I'll probably just use one sometimes. But this is equal to, and you can have some other expression followed by some other expression, or could be some different expression or something else. So this is concatenation. We're saying a name, it would be an expression 1 followed by an expression 2. This is an or, just like in C. And we can also have things inside quotation marks to represent an actual symbol. So this is a symbol. And it's mostly self-explanatory, and we're not going to be super rigid about this, but this is the general form of the statements we'll be dealing with. So something on the left, we're defining whatever that name is and saying that it can be any of these things separated by ors. In this case, expression 1 followed by expression 2, or expression 3, or whatever else, or maybe just the character z. And sometimes we'll say, or it could be an empty string. So that's our good old lambda, empty string. And not everything can be an empty string, but sometimes that'll be useful. So let's look at a BNF for something real. So this is BNF for an expression. And in particular, I want to look at an assignment statement. So, and I'm going to skip these angle brackets in here. So I'm going to define what an AS is. That's an assignment statement. And an assignment statement is the following. It's a variable followed by an equals sign followed by an expression. If we insisted on a semicolon, we could put a semicolon at the end, but simple assignment statement. So variable equals some expression, right? And this does us no good unless we know what a variable is. So what is a variable? Well, what do we think of as being a variable? It's a string of letters and numbers, right? And you have to have at least one symbol. And usually the first symbol can only be a letter. It can't be a number. So we'd like to write BNF for that kind of variable. So a variable could be a letter followed by what I'm going to call a variable 2, or it might just be a letter. And a variable 2 is going to be what I call a symbol followed by a variable 2, or it's just a symbol. And a symbol is either a letter or a digit. And a letter is an A or a B or a C or a Z, and a digit is a 0 or a 1 or a 9. So what kinds of things can be a var in this BNF? Well, clearly a var can be a single letter, so an A through a Z. That's a valid variable. Or it could be a letter followed by a var2. Well, what's a var2? A var2 is a collection of letters or digits. Okay, it could be just a single symbol, which is a letter or a digit, or it could be a letter or a digit followed by another var2, which is one or more letters or digits. So a var2 is capturing the idea of one or more letters or digits, right? And we're saying a variable is either a letter followed by one or more letters or digits, or it's just a single letter. So that captures our general notion of variables, ignoring underscores. Combinations of letters and digits beginning with a letter. So that's the left side of this. So it's one of these things we're calling a variable, followed by an equal sign, followed by an expression. Now expressions are more interesting because we can do plus, minus, times, divide, and we can do parentheses. And we have to be able to match parentheses. For example, this should be a valid expression. This should be a valid expression. And that should be a valid expression. But this is not, because the parentheses are unmatched. And this is not because the parentheses are unmatched. And that's not because we're missing something after the operator and so on. So we want this to capture all of those syntactical nuances. And it's actually really easy to do with this approach. So try this. An expression is an expression followed by an operator, followed by an expression, or a parentheses followed by an expression, followed by a closed parentheses, or a variable, or a number. So an expression could be just the name of a variable, sum, total, answer. Could be a number, 2, 5, 12, -6. It could be an expression inside parentheses, or it could be two expressions with an operator in between. And ignoring the recursiveness of this, right? This is an expression, an operator, and an expression. So this whole thing is an expression, followed by an operator, followed by another expression, makes this whole thing an expression. And an expression inside parentheses is also an expression. So this thing is an expression. There's an operator, another expression. So all of this is an expression, and that's all inside parentheses. So that's an expression. There's an operator and an expression. This whole thing's an exp. An expression inside parentheses is also an expression. There's an expression, operator, another expression. This whole thing is an expression.
If you needed to specify, like, because those are all binary operators, if you want to get into urinary and ternary, would you change that statement to say expression? Or would you go into, like, defining what each type of operator would be?
So we could also make an expression a minus sign followed by an expression. And that would pick up the unary minus. And I never thought about ternary, but with the question mark, it would probably be pretty unambiguous. All right, well, what's an operator? So we'll just do plus minus times divide. And a variable we've already described. So what could we do for a number?
Would you like asking us to find if it's a number, right?
Mm-hmm.
Could you say int or something? Or like, actually, I'm trying to think how to do this with code.
It could be a digit followed by a number, or a digit, just a single.
Cool. So a digit followed by a number or a single digit. That means we have to have at least one digit. But if we do, then it could be followed by something else with at least one digit. So that's a succession of digits. So that's definitely a collection of digits. Cool. All right, what about negative numbers?
Oh, you have to have some kind of expression before the thing.
So let's make this a num2 and say a num is a minus sign followed by a num2, or it's just a num2.
So it would have to be a num2 in.
That's a num2, correct. All right, you're getting the idea. So do we have anything else we need to define here? We got operators, variables, numbers, symbol. I don't care about symbols. We did symbols, letters or digits. Cool. All right, so there's a description of an expression. And it turns out if you use this to parse an expression, you can also use it to evaluate the expression. Because what do parentheses do? They say you should evaluate the thing inside the parentheses first. Well, as you're taking a string and applying this BNF to see if it's an expression, at some point you're going to find out that what you have is a parentheses, an expression in a parentheses. And once you evaluate the value of this, right, and you've got a parentheses before and after, that becomes another expression, and that gives you the value of that parenthesized expression. And then if you're going to take an expression and operate on another expression, you're going to know it's an exp and op and exp. And if you remember what your operation was and what your two expressions were, you can actually do evaluation with this. And it almost writes itself once you have a good BNF, which is kind of cool. So let me see if I can find one of these quickly. So here's the C language. And it's not that long. It's a little long. But it's a lot smaller than like the C primer. right? And this tells you the complete specification of the C language, right? Every nuance, do I need a semicolon here? Do I need a curly bracket there? Is captured in this description.
Scott to get all the new kids started on.
Yeah, yeah. We could print it on T-shirts and like hand it out in orientation. All right, so BNF is fun if you're into that kind of thing. It's a fun way to play with languages and syntax. And I didn't get my code together, but I'll show you some code tomorrow that uses a BNF style description to do some parsing and do some syntax checking. The other nice thing when you have a BNF is if you're parsing a string to see if it's, say, an assignment statement in this case, you keep moving down the string and trying to apply different pieces of this. At the point where you find that none of these rules apply, if you look as far as you got in the string, chances are that's where your syntax error is. So we got a parenthesis and we got an expression, we never found the closing parenthesis. Chances are that spot where we were expecting a closing parent, that's where the syntax error is. Give or take, right? You can do something wrong over here and it causes an error out there. But in general, it lets you sort of nail down the location of the issue pretty closely. Oh yeah, yeah. So Bootstrap is interesting, right? So the first C compiler, well, the first compiler of whatever language was first, Algol or whatever it was, right, had to be written in assembly language. Well, let's go back to assembly language, right? There was a time when there was no such thing as an assembler. Everything was written in machine code, and you knew what the instructions were, and you just wrote out the binary or the hex for each instruction. You figured out where to branch to for each branch, and you typically toggled this into a machine using a bunch of switches, right? This is a fun exercise because if you make one mistake, you go back to the beginning and you start over, right? But you've got this idea of like, it would be cool to be able to write assembly language and not have to deal with all the ones and zeros like you do in 270, right? You can say increment, file register. But the first assembler had to be written in assembly language, in a machine language, right? Because there was no assembly. But once you have that first assembler, you can rewrite it in assembly and then assemble itself, right? And then the same thing with C. If all you have is assembly language, your C compiler is written in assembly. But once you have a C compiler, you can write a new C compiler in C and feed it to itself to compile it. And now you've got a better C compiler. And there's this whole Bootstrap sequence that you need for any technology. But you only have to do it once. And as long as no one loses the last C compiler, we can always write our stuff in C now. So what? Yeah, exactly. Which it used to be. Not for C, but for other languages. Actually, Unix used to be a very closed system. It was like $40,000 to buy the source code, plus a stack of licensing agreements you had to sign. All right. Well, this takes us to everyone's favorite topic, which is finite state machines. So flashbacks to Engineering 250, right? We're not going to do the big, long, wide state tables with previous state and inputs and next state and flip-flops and truth tables and K-maps and all this kind of stuff, okay? We're skipping beyond that level of things. We're looking at a much higher level here. But it's the same concepts that we used in 250. So what's the idea of a state machine? It's a system that has some notion of state. State is just kind of the essence of the machine, its current condition, which could be the value of memory locations, but it's somehow the current condition of the system. And the future condition of the system, the future state, depends on its current state and usually on a set of inputs. Okay, so current state plus inputs gives you next state, and typically plus some outputs. So when we do this in 250, we make this table, and our original inputs are current state and inputs, a bunch of stuff in the middle, and our final outputs are next state and outputs. Is that familiar? Okay. So same idea here, and all of this stuff is clocked in some way. There's some ticking clock that every time it ticks, that's when we actually move from our current state to the next state. And the stuff that happens in between these ticks is usually ignored. And it's a finite state machine because our set of states, present, next state, and so on, is finite. Okay, an infinite state machine is a lot harder to build because you need an infinite number of flip-flops. So we'll stick with finite state machines. So basically it's present state and inputs, and then clock ticks, and that takes you to a next state, and outputs. Right, and after the clock ticks, that next state becomes your present state. And whatever the current inputs are evaluated on the next clock tick to give you a next state and new outputs. And we can go mathematical on this and say this machine is a 6-tuple, which we'll call S, I, O, F, G, and S0. We don't really need to do this, but we will anyway. So S0 is a set of states. I is your set of inputs. O is your set of outputs. S0 is your initial state. So it's an element of S. And then F takes a state and an input and gives you a new state. So that's your state transition function. And G takes a state and an input and gives you an output. But that's just mathematical formalism. So let's have fun with this instead. Let me mention one other thing, though, here. Not that we're going to dwell on this in this course, but if you missed this in 250, let's pick it up here. So if your output depends on your current state and your inputs, that's what we call a Mealy machine. It's also possible that your output function only depends on your current state, and that's what's called a Moore machine. What's the difference? With a Mealy machine, you might be in a particular state, and even without the clock ticking, if your inputs change, your outputs might change at the same time. Okay, that's the characteristic of a Mealy machine. With a Moore machine, your outputs will only change when the clock ticks, because they only depend on the current state. So we're in a current state, our inputs are changing, but our state's not going to change until the clock ticks. In a Moore machine, our output is totally stable. Okay, we're not really going to worry about that distinction. We'll mostly deal with Moore machines. And you can turn one into the other pretty easily and mechanically, but if you missed it in 250, there's the difference between Mealy and Moore machines. All right, so favorite state machine example. Here's the mood machine. Anybody here not taking 250 yet? You taking it in spring? If you take it with me, we're going to build a mood machine on an FPGA. All right, so here's the mood machine. So it's got 4 states, and we're going to capture the way that we move from one state to another with a diagram, okay, state diagram. So this state up here we're going to call very happy. This state we're going to call happy. This one we're going to call sad, and this one we're going to call very sad. And we're going to have a single input. Okay, so we'll make a little key here. And the input is W. So W is 0 if it's rainy, and it's 1 if it's sunny. So that's our weather input. So here's how we transition between states. So let's say we're in the very happy state, and suppose it's sunny. We're going to remain very happy because we like the sun. So if our input is a 1 and we're very happy, we're going to stay happy. But if our current state is very happy, but it's raining today, we're still happy, but we're not very happy. But we're still definitely happy. And if we're happy and today it's sunny, well, that's going to make us very happy. But if we're just kind of happy and it's raining again, so our clock is each day when the sun comes up, right? If we're happy and then the next day it's raining again, now we're going to transition to being sad. And if we're sad and it rains the next day, that's going to take us to being very sad. And if we're very sad and it rains the next day, we're still going to be very sad. I really like the rain, but this works. All right, and the other direction the same way. If we're very sad and it's sunny, that doesn't make us totally happy, but it changes us from very sad to just sad. And if we're sad and then it's sunny, now we're happy. And if we're happy and it's sunny, then we're very happy. And we have 4 states, and we can transition between these states based on this one input, which is the weather. So it's a 1 or a 0. So that's an example of a state machine. And we can build hardware to create a machine that performs these functions, and we would have 4 possible states. So we'd have 4 pieces of memory, right? Typically a 2-bit memory with 4 possible values corresponding to these, and an input and a clock, and every time the clock ticks, the state and the input are examined, and you go into a new state accordingly. And we could make a transition table. So present state, input, next state. And let me just label these states VH, H, S, and VS. So if you're very happy, your input could be a 0 or a 1. If you're happy, your input could be a 0 or a 1, and so on. So very happy and a 0, your next state's happy. Very happy and 1, your next state's very happy, and so on. All right, so that's the kind of state machine we do in Engineering 250. And we're not going to worry about how to build this in here, but 250 you do. So the mood machine actually turns out to be something called a 2-bit branch predictor. And you find these inside CPUs, especially things like ARM processors, things that rely on pipelining. It's a way to predict whether a conditional branch is going to be taken or not. And the way branch prediction is usually done is you look at the last time you came to this conditional branch. So this is saying, you know, if x is 0, you branch to this direction. And you don't know until you actually get to that instruction what the value of x is, if you're going to take that branch or not. But you can try to make a guess. And the way you make a guess is you say, the last time that we executed that conditional branch, did we branch or not? Okay, so this is the condition where we strongly believe we're going to branch. We sort of believe we're going to branch. We sort of believe we won't branch, and we strongly believe we won't branch. And if we think that we're going to branch and you do branch, you stay there. If you think you're going to branch but you don't, then you move over here to where you sort of believe you're going to branch. And if the next time you still don't take that branch, then you come down here to where you think you're probably not going to branch. And if you don't branch that time, then you come to where you strongly believe you won't, and so on. So it's the same state diagram, but it lets you do a decent job of predicting whether or not future branches are going to occur or not. And that comes into the whole idea of pipelining. And this is a 270 topic, so we won't get into it here. But basically, modern processors, they break up an instruction into a bunch of little pieces. And you're doing this piece of the first instruction, you're doing this piece of the instruction before, you're doing this piece of the instruction before that. And you might break an instruction into 8 or 13 or 20 pieces. And effectively, you multiply your clock speed by however many pieces you have in your pipeline. But if you think that you're going to execute this instruction, but when you get down here, it actually says, okay, let's take a branch over to here, right? All of the pre-execution that you did on these instructions is wasted. And you get what's called a pipeline flush. And now for the next 8 or 13 or 20 clock cycles, nothing is finishing because you're starting with a new instruction stream over here. So branch prediction is really, really important on these deep pipeline systems to keep your throughput high. That's how you keep your effective rate very high. All right, so that's one application of the mood machine, right? 2-bit branch prediction, and that's a real thing. All right, let's look at another machine and see what this does. So this is going to be a machine with 2 states, state S1 and state S0. And I'm going to put a star here, and the star means this is the initial state. So this is the state the system begins in. And I'm going to have a key for what's happening here. And on each of these transition arrows, I'm going to have an input and a slash and an output. Okay, the idea is you're going to feed in 1s and 0s to the system, and it's going to spit out 1s and 0s. Okay, so the thing you feed in determines which arrow you take, and the thing it spits out is whatever comes after that slash. Bless you. So here's what our machine looks like. State 1, you get a 1, you output a 1 and go to state 0. State 1, you get a 0, you output a 0 and go to state 0. State 0, if you get a 1, you output a 0 and go to state 1. And state 0, if you get a 0, you output a 1 and you go to state 1. So the question is, what is this machine doing to its input? So we know we're starting in state S1. So let's, anyone got an idea first?
Well, I'm thinking like, hold down the button, it's just going to toggle between the two.
Okay, so let's suppose our input, let's do it like this.
Well, maybe it was some kind of encryption device or something.
Could be. Suppose our input is a bunch of 1s. So what's the first thing it's going to do, so we're starting off in state 1. Clock ticks, what's going to happen? It's going to output a 1, and it's going to move to state S0. All right, next clock tick. We're still inputting a 1, what's it going to do? It's going to output a 0, go back to S1. And the only thing that affects the behavior of this is what our current state is and what the input is. So once we know what happens when we're in state S1 and this input, we can just keep repeating this, right? So it's going to keep outputting 1, 0, 1, 0, 1, 0. All right, what if our input was a bunch of zeros? What's it going to output? It's going to do a 0, go to S0, and then that 0 is going to output a 1, go back to S1. So it's going to output 0, 1, 0, 1, 0, 1. So what if our input's something random like this? Say again? You see a pattern?
Oh, yeah, yeah, it's like essentially a current state.
So you're always going to alternate every even bit.
Okay. Right. So if you're in your initial state, it's going to output whatever you input. Right? So this is just going to be whatever that bit is. And it's going to go to S0, regardless of what you input. And if you're in S0, it's going to output the opposite of what you input and go back to state 1. So this is the opposite of that bit. That's the same, that's the opposite, that's the same, that's the opposite, that's the same, that's the opposite. So in general, if your input is a series of bits, your output just complements every other bit. So it toggles a second, fourth, sixth, eighth bits, and so on. Is that? Yeah, if you send it through again, it undoes it. So is it useful? I don't know, but it's an example of a state machine. All right, let's look at one with 4 states. Actually, I'm going to give this one to you to think about, and we'll talk about tomorrow, because this is a good one to work through. So go ahead and write this down. All right, our initial state is S00. So here's what it does. 0 gives you a 0 and stays there. 1 gives you a 0 but changes to S01. Another one gives you a 0 and changes to S11. Zero gives you a 1. Zero gives you a 1. Zero gives you a 0. 1 gives you a 1. Am I missing any? This is 0, 1, 0, 1, 0. I need a 1 from there. So 1 gives you a 1, and 0, 1. There we go. Got 8 lines, we're good. Okay, so what does this do to an input string? So play around with this outside of class. Feed some strings into it and see what it looks like it might be doing, and then think about the state transitions and see if you can come up with a description of what this does. And it's got a pretty succinct description if you figure it out. So that's one to play with. I'll keep that. So. All right, another thing we can do with state machines is language recognition. Just like BNF, just like parse phrase grammars, we can do language recognition. So here's an example of a state machine. So this is our initial state S0. We have a state S1. And we have another state S2, and I'm going to draw it with an extra circle around it. And there's no outputs produced from this, there's just inputs. So this double circle, this is what we call a recognized state. Whenever you're in the recognized state, it means that the input you've seen up to that point is recognized as part of your language. Okay, so anytime you're in a recognized state, input up to now is part of the language. So if we were building a state machine to recognize an assignment statement, when you got to a recognized state, a state with an extra circle around it, it would mean that everything you saw up to that point is an assignment statement. So the question here is, what kind of strings will this machine recognize? We're starting in S0, we're getting in ones and zeros. What sorts of strings will take you to state S2? Okay, so a 1, 0 will take you to S2 because a 1 will take you here, a 0 will take you there. A 0 will take you directly to S2, so that's a part of the language also. What else? We did 1, 0.
Oh, sorry, 1, 1.
1, 1. Right, that gets you there. Yeah, so 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, right? Any number of zeros or ones after a recognized string will also be recognized. So it's a big language, and we could write this as 0, 1, 0, 1, 1, followed by 0 or more occurrences of either a 0 or a 1. And this is a shorthand that we can use. And the shorthand works like this. Suppose A is a set containing just 0 and 1. So if we write A with a number on top, it means all the strings of that length comprised of symbols from the set A. So what are all the strings of length 0 containing zeros or ones? There's only one. It's just lambda, it's just the empty string. All the strings of length 1 comprised of symbols from A. There's exactly 2 of those. The string 0 and the string 1. A2 is the set of symbols of length 2. So there's 4 of those, and so on. And A star is the union of all of these. So that's the set of all strings of any length, 0 or greater, comprised of symbols from the set 0 or 1. That's the star you get in grep and other regular expressions. When you say something asterisk, it means 0 or more occurrences of that thing. Same idea. So there's a regex-ish kind of way, to describe the language recognized by that machine. Rish, that works. All right, let me show you one more. So this is our starting state. Here's our recognized state. There's a 0. There's a 1. There's a 0. There's a 1. Yeah, can't claim to know what this does exactly. So what's going to be recognized by this?
So it has to have odd number of zeros,
Okay,
and but the ones are very hard to describe.
so if we have a bunch of 1s in the beginning, that's not recognized, right? If we have a 0, suddenly that's recognized. And if we have more 1s, it's still recognized. But if we have a second 0, then it's unrecognized.
That's all it is then. It just has to have an odd number of zeros.
It's just a string with an odd number of zeros. And again, it's a finite state machine, but it will recognize a string of any length and tell you whether or not it has an odd number of zeros. You could feed in a string with 1,000,001 zeros, and it will still tell you, okay, that's got an odd number of zeros. And there's no upper bound on that. It's not like a C program where you could just be counting and incrementing it, eventually overflow at 4 billion, right? This will work for not an infinite length string, but a string of any length. Subtle distinction.
Can you have your starting string also be your recognized state?
Sure, yep, yeah. Which would recognize the empty string, among others. All right, so think about that machine, and I'll think about it and make sure I understand what it does too. We'll play a little more with language recognition machines, and then we're going to talk about Turing machines tomorrow. So that's the real fun part of this topic. All right, so we'll start from there tomorrow.